We'll start today with start this video with a warm-up question. Write a differential equation that could be used to model exponential growth and another to model exponential decay. What are these two equations that you have in common, and what is different about them? So take a minute, pause the video, and then unpause when you're ready to go over. So I'll assume that you've paused and unpaused and you're ready to go over. So generally speaking, when you have a differential equation that's modeling exponential growth, this is going to be something of the form dy dt is equal to k times y. It's saying that the rate of change is proportional to the population present. So k is going to be your growth rate. So if your population is increasing by 5% each year, then you'd have dy dt is equal to 0.05 times y. And if it's decreasing by like 7% each year, you might have something like dy dt is equal to negative 0.07 y. So over here we have exponential growth, and over here we have exponential decay. And so what do they have in common? So they're both of this same form, dy dt is equal to k times y, where k is just some constant. But the difference is in the sign of that growth rate k. If it's growth, it's going to be positive. If it's decay, it's going to be negative. You might also ask what happens in this model if like k is equal to 0. So if k is equal to 0, you'd have like dy dt is just equal to 0 times y, so just 0. So that would tell you that the rate of change is just always 0, and so your population or whatever y represents is just remaining constant. So if your population is like 100,000 and dy dt is just equal to 0, then that would say that your population is just always going to stay at that fixed number, 100,000 or whatever I said. So let's move into new stuff. So related rates is going to be the section for today. So we'll start with a warm-up example. Okay, so let's say that we have a square pond with side length 10 meters. The pond is expanding and remains square, with its side length increasing at a fixed rate of 2 meters each year. Let's let S represent the side length. So right away, if S represents the side length, then it's increasing at 2 meters per year, so ds dt is equal to 2. And let's let A represent the area, and T to represent the time in years. So initial question, is the same amount of area being added to the pond every year? Why or why not? So if we just want to visualize this, just using square. So here we have some square. We'll say that the side length of the square is 10 meters. And then let's increase it by 2 meters, like so. So how much does the area go up by? Just visually, you can kind of see it would just be this area right here. Right, so you could calculate this as like the area of like two little rectangles added to each other. We won't bother calculating exactly just yet. But then if we increase it by another 2, we'll end up adding this much area to the pond, right? So visually you can kind of tell that the first year we're only adding this much area, and then the second year we add this much area, and visually the amount of area that's being added after that year is going to be a little bit higher. And then if we just kept adding 2 meters, the amount of area that we add each time is just going to go up and up and up every time. All right, so let's calculate the side length and area of the pond at t equals 0, 1, 2, and 3 years. So I'll put a I'll make like a little table. So we'll have one for t, one for the side length s, and then a column for the area a. So t is 0, 1, 2, and 3. At time t equals 0 years, our original side length is just going to be 10. And the area, since the area is just equal to the side length squared, area is 10 squared, which is 100. After 1 year, our side length s goes up by 2, so it's going to be 12. And then our area will be 12 squared, which is 144 square meters. After 2 years, we'll be at 14. After 3 years, we'll be at 16. 14 squared is 196. 16 squared is 256. So now we can actually explicitly say how much our area is going up by each year. Plus 44, plus 52, and then plus 60. That's how much our area goes up by from 0 to 1, and then 1 to 2, and 2 to 3 years. And so these numbers can help us sort of estimate what dA dt is at various points here. All right, so at t equals 0, dA dt is like roughly 44. At t equals 1, it's like roughly 52. Maybe you could like be a little bit more precise by saying it's like probably some number between 44 and 52, like 48, for example, and so on. Okay, so related rates is all about this. So we have ds dt is equal to 2, right? So we know something about this rate, the rate of change of the side length, and we want to use that information to say something about how much the area is changing using some equations and some like known values in the problem, right? So let's do that. So let's say, what do we know about SA and ds dt? And let's use all that information to determine the rate of change, the exact rate of change of the area of the pond after 2 years. So we're able to estimate it just using this table, right? But we don't want to like rely on estimations for all of our answers. We want to be able to do this in a more efficient and exact or precise way. So at t equals 2, we can say that S is equal to 14, right? Just from the table, and the area is going to be 14 squared, which is 196 square meters. And we also know what ds dt is because that's fixed to be 2. All right, that's just told to us in the problem. So we're asked, what is dA dt equal to? So to approach this, what we'll do is we'll start with an equation relating a and s squared. Sorry, relating a and s. And that equation, of course, is just saying that the area is just equal to the side length s squared. So this is just a basic equation relating the variables a and s in our problem. In other problems, you might have like somewhat more complicated equations. Maybe you have something like 2a cubed plus a times s is equal to 50s to the fourth or something like that. Just some equation that relates all the variables. And then what you do from there is just take the derivative ddt of both sides of the equation. So what's dt of a? That's literally just dA dt. What is the derivative with respect to t of s squared? So using implicit differentiation, a little bit of a chain rule here. The derivative of s squared is 2s times ds dt. And so now, once we have this equation relating our known quantities, we just do implicit differentiation, and now we have obtained an equation relating the rates of change of those quantities. Now we can just use all of this information over here, plug in all of our variables that we need, and then solve for what we're looking for. So dA dt, let's do black. So dA dt at t equals 0, sorry, at t equals 2, is going to be equal to 2 times our side length s, which was 14, times ds dt, which was known to be 2. So this would be equal to 2 times 14 times 2, which is 28 times 2, which is 56. If we wanted to put some units on here, that would be in square meters per year, because this is talking about how fast the area is changing with respect to time, right? Side length is going up by 2 meters per year, so area should go up by square meters per year. Let's check if that matches like our intuition from over here. Well, at t equals 2, from t equals 1 to 2, went up by 52, and then from 2 to 3 went up by 60. So the instantaneous rate of change at t equals 2, we would expect to be some number between 52 and 60. We got 56, which is just smack in the middle of those two, right? So 56 just happens to be the average of those two numbers. It's not always going to work out that nicely, right? This is like a pretty basic example, but you know, that's sort of confirming some intuition for us. So let's work on a slightly more involved example. All right, so we have a spacecraft which launches from the ground and travels vertically. A person stands 3 miles from the launch point and watches the spacecraft rise. 20 seconds after the launch, the angle between the ground and the person's line of sight to the spacecraft is pi-thirds radians, and it's increasing at a fixed rate, or maybe not a fixed rate, but at that point it's increasing at a rate of 0.11 radians per second. Let's assume that the person's view is from the ground. So in other words, we can ignore their height. Typically their view would be, I don't know, like 5 or 6 feet off the ground. But we'll ignore that and find the spacecraft's velocity at that instant in miles per second. All right. So whenever I'm doing this, the goal is to find an equation that relates the quantities involved. Maybe it's misleading to say start by doing that, because really to get there, you want to start by drawing a picture. So let's draw a picture. So we have person, and then there's a launch point 3 miles away. And then way above that is a spacecraft. And then we have some distance from the person to the spacecraft. So a little rocket up here. Boop, 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 boop. Some fire. Great, there's our rocket. All right. So the rocket is going to be some number of feet off the ground, or miles off the ground. All right. Let's talk labeling variables in our picture, in our diagram. So this distance from the person to the launch point is told to us to just be fixed to forever be 3 miles. So there's no sense in like calling this like X or something like that. Like we don't need to like assign this a variable because it's not a variable, it's a fixed quantity. So we'll just, in our diagram, make that a fixed number. Conversely, well, okay, what about this angle over here? So it says that 20 seconds after the launch, the angle between the ground and the person's line of sight is pi-thirds radians. So this angle at that point in time is pi-thirds radians. However, as the rocket continues moving upwards, that angle is actually going to increase, right? So we should, because this angle is changing, assign it a variable. We'll call it theta to represent that angle. And then just say at t equals 20 seconds, theta is equal to pi thirds radians, and d theta dt is equal to 0.11 radians per second. Okay, cool. Are there any other variables which we should label in this diagram? So there's all sorts of things that we could label. Like we could label like this side length C over here. We could label this side length H over here. We could maybe label this angle over here. But not all of those quantities are going to be important to our problem or to our diagram, right? So the only one that's really going to be important here is the height of the rocket, because we're just asked find the spacecraft's velocity at this instant in miles per second, and it's traveling vertically. So we're really asking what is dh dt equal to. So the problem is asking us to find dh dt. So we'll just label this, and this is a sufficiently good diagram for our needs. Now we need to find an equation that relates the involved quantities of theta and h. And to do that, we can use a trig function. So there's a couple trig functions that you could go about using here. Technically, all of them could work. But the most efficient one that you can use is tangent. So you can say that tangent of theta is equal to opposite over adjacent. So that's just going to be h over 3. And so this is probably the most, the cleanest equation that you could get that relates these two variables to each other, right? You could do something like with cosine, like you could say like cosine of theta is equal to like 3 over whatever that variable c is, and you could solve for c like in terms of h. That would still technically relate it. Or you could do something with like sine of theta as well. But again, those would just be like kind of complicated compared to like what we can have over here. The point I'm really trying to make here is that there's no one way to do these problems a lot of times. A lot of times there's multiple ways to approach the problem and get to the same final answer. So if your process looks different from my process, there might not be anything wrong with that. Like your process might still also be correct. All right. From here, we just want to use implicit differentiation to get an equation that relates the rates of change, dh dt and d theta dt. So the derivative of tangent is secant squared theta times d theta dt by the chain rule. And then remember that h over 3 is really the same thing as 1/3 h. And so the derivative of 1/3 h would be 1/3 times dh dt. So this is our equation relating the rates of change. And now we can just plug in all of our known information to find dh dt. So dh dt, we can just multiply through by 3 here and get that dh dt is equal to 3 secant squared theta d theta dt. And then plug in this information. 3 secant squared of pi thirds times d theta dt, which is 0.11. And now we might as well go that extra mile and compute secant squared of pi thirds. So our pi thirds triangle looks like this. So it's 1, 2, square root of 3 triangle. And so secant of pi thirds is equal to, well, I always think of it as like the reciprocal of cosine. Cosine is 1 over 2, so secant would be 2 over 1, or just 2. So secant of pi thirds is just 2, or 2 over 1. So this becomes 3 times 2 squared times 0.11. 3 times 2 squared, 3 times 4 is 12. 12 times 11 is 132. But then we're multiplying by 0.11, so we would move the decimal over 2 spots. So 1.32, and this is miles per second. All right, awesome. So we could also ask sometimes like, it might be more useful to have like an answer that's given in miles per hour. If you want to do something like that, you just want to do a simple unit conversion at the end. So over here, 1.32 miles per second is equal to what? So we can do some unit conversions. So we want to multiply by how many seconds there are in like an hour, or you could just do seconds to minutes. So there's 60 seconds in 1 minute, and then convert from minutes to hours. There's 60 minutes in 1 hour. And so multiplying by these unit conversion things, we would cancel out like our seconds and then have how many miles per minute we're going, and then multiply by 60 minutes in 1 hour and get that many miles per hour. So we get 1.32 times 60 squared miles per hour. I'm not going to bother putting this into a calculator, but of course you could if you wanted a more precise answer. Let's do another problem. A chemical reaction produces a gas in the form of a spherical bubble at a rate of 2 cubic inches per minute. How quickly is the radius of the bubble increasing when the radius is 10 inches? So just to see if you're kind of following along, I want you to know which of the following equations is going to relate the rates in this problem. So you're told that the volume formula for a sphere is V equals 4/3 pi r cubed. So based off of this equation, which of the following relates the rates in the problem? All right, so take a minute and try to answer the problem on your own, and then unpause, come back. All right, assuming you've had a chance to try this, we want to take this equation and just use implicit differentiation, take the derivative with respect to t of both sides. The left side will just get dv dt. On the right side, we get 4/3 pi times 3r squared. Derivative of r cubed is 3r squared. And then times dr dt. Of course, these 3's will cancel. We're left with 4 pi r squared times dr dt, which is what shows up over here. So we would have dv dt is equal to 4 pi r squared times dr dt. And so our answer would, in fact, be D. Okay, so implicitly differentiating, we get dv dt equals 4 pi r squared dr dt. All right, so let's use this now to finish out the problem. All right, so a chemical reaction produces a gas. Blah, blah, blah. All right, so we have this. We don't really need the picture. We already have the equation, but I'm just going to put it there anyway. Just so I like visualizing things. All right, so the rate is 2 cubic inches per minute. So that's telling us something about the volume, right? Because you can tell that this is a volume measurement because it's in cubic inches per minute. So dv dt is equal to 2 cubic inches per minute. And we're told that the radius is given to be 10 inches at that point. All right, so now we need to find how quickly the radius of the bubble is increasing. So we need to find dr dt at that point. So plugging all this information in, we get dv dt, which is 2, is equal to 4 pi times r squared times dr dt. And now we just solve for dr dt just by dividing all this over. Get dr dt is equal to 2 over 4 pi times 10 squared, 4 pi times 100. The 2's can cancel. This is like 1 over 2 pi times 100, or just 1 over 200 pi. And this would be in inches per minute. So our radius is increasing by 1 over 200 pi inches per minute at that point in time. All right, let's do another one. So this one I think is pretty challenging in terms of like getting the equation that relates all the known quantities. So a tank has the shape of an inverted triangular prism. It has a height of 5 meters, a rectangular top with some side lengths, and then the tank is initially empty, and then we begin pumping water in at a rate of 0.7 cubic meters per minute. And then it asks us an initial question, but let's maybe get a picture going before we look at that. So inverted triangular prism. Let's draw a little triangle. See if this snaps. It's not snapping. Let's try this instead. Do that. All right, so this is our inverted triangular prism. You got a triangle, and then you just kind of thicken it up a bit, and then you get a triangular prism, and it's upside down. It's inverted, right? All right, it tells us that the height of this is 5 meters. And the top is rectangular with side lengths 6 meters and 12 meters. All right, so we have this side length, and then the distance from like the ground to the top. All right, great. All right, and then we're pumping in some water at a rate of 0.7 cubic meters per minute. And so that should tell us that, you know, after some amount of time, we have some amount of water tank. So it's going to look like that. Look like that. Let's see if I could just copy paste. Shoot. Yeah, that's good enough. And then we're filling it up with water. So this is all full of water. Great. And let's give this a variable, like the height. So like there's like another triangle, like what's like the height of the water in the tank here. So that's going to be that height h. All right, so let's ask this initial question. Answer this initial question before we computed everything. What should intuitively happen to the rate of change of the height h as the tank fills? So over time, what is really happening to dH/dt? Is it getting bigger over time, or is it getting smaller over time? Well, intuitively, like once you start pumping water in there, so if you pump in a little bit of water, it's going to make it go up by like a lot because it's easy to fill up the tank here at the bottom. But as you get like higher up, higher heights, you're pumping in water at like the same rate of 0.7 cubic meters per minute. And so because you have more space to fill up, the height is not going to go up by as it's not going to go up as quickly. So dH/dt is getting smaller over time. That's repetitive. All right, cool. So now let's actually start computing things. So how quickly is the height of the water level rising when the height is 1 or maybe 2 meters? So let's start by getting an equation relating the height and the volume, right? So we're told that dv dt is equal to 0.7, and we're asked to find dh dt for various heights. So like a height of like 1 meter and a height of 2 meters. So let's get an equation relating h and v. Well, the volume of the amount of water is going to be equal to the volume of like this little blue area, which is going to be, so for a prism, it's going to be the area of the base, and the base is just going to be that base triangle over there, and then times the height of that prism. The height of the prism is really the length of the prism, I guess, so it's just going to be 12. So this times 12. And now we just need to figure out the area of that triangle. Well, area of a triangle is going to be 1/2 base times height. We have the height here, but we don't know what the base is necessarily yet. So let's maybe assign a variable to that for now and kind of hope to eliminate that, because we don't want too many variables floating around here if we don't have to. But for now, we can just say that this is 1/2 base times height times 12, or 6 times base times height. 12 times 1/2 is 6. All right, and so now what can we say about B? Well, this triangle right here, notice that this triangle is actually similar to this triangle over here. And the base and height of this triangle, the base is 6 and the height is 5. So the base and the height should be in proportion with the base and the height of that similar triangle. So there's any number of ways that you could set up a ratio relating all those quantities together. One way that you could maybe do this would be, let's see, the base of the smaller triangle divided by the base of the larger triangle is equal to the height of the smaller triangle over the height of the larger triangle. So base over 6 is equal to height over 5. And so the base is equal to 6 times the height over 5. So then our equation would be v equals 6 times the base, which is 6h over 5, times that height, or just v equals 36h squared over 5. All right, so now we have our equation relating v and h. We have to do implicit differentiation to relate the rate of change of the volume and the height. So dv dt is equal to 36 over 5 times the derivative of h squared, which is 2h times dh dt. So 2h times 36, that's going to be 72h over 5 times dh dt. And now we can use this to figure out what dh dt is. So dh dt, I can just divide all this stuff over to the left-hand side. dh dt is equal to 5 over 72h times dv dt. And so at a height of h equals 1, dh dt is equal to 5 over 72 times 1 times dv dt, which is told to us to just be 0.7. And at h equals 2, dh dt is going to be equal to 5 over 72 times 2, all times 0.7. And that's the problem. All right. Pivoting to a different problem. This one's about boats. Two boats begin moving at the same time from the same location. Boat A is moving west at some speed, and boat B is moving north. Let's find the rate of change of the distance between the two boats after 2 hours. All right, so boat A is moving west 11 miles per hour, and boat B is moving north at 8 miles per hour. So we'll call this distance over here A, and then this distance over here, call it B. A represents like how much distance boat A has traveled. This represents how much distance boat B has traveled, right? And then we'll call C the distance between boat A and boat B. All right. So we are told that dA dt is equal to 11 because this distance is growing at a rate of 8 miles per hour. Similarly, dB dt is going to be equal to 8, increasing at a rate of 8 miles per hour. And we're asked to find dC dt. At a time of 2 hours, we can also say what A and B are equal to. Here, A is it's increasing by 11 miles per hour, and they're starting at the same time from the same location, right? So A is going to be equal to 22, just 11 times 2, and B is going to be 8 times 2, which is 16. We now want an equation that relates A, B, and C. And so the Pythagorean theorem is going to be the one that does that. So A squared plus B squared is equal to C squared. And now we want to use implicit differentiation to solve or to get an equation that relates dA dt, dB dt, and dC dt. So taking derivatives of everything, derivative of A squared is 2A times dA dt plus 2B times dB dt. And this is equal to 2C times dC dt. We could go ahead and, because every term has a 2 in it, just divide through by a 2. And now we can solve for dC dt just by dividing through by C. So we get A dA dt plus B dB dt, all divided by C. And now we just plug in all of our information. You might notice a problem over here. So we listed dA dt, dB dt, and then A and B, but we don't know what C is equal to. So we need to be able to plug in C. So we're actually going to need to go back to this equation that relates A, B, and C and use that to solve for C. So C is going to be, in this case, just the square root of A squared plus B squared. So square root of A squared is just 22 squared, B squared, which is 16 squared. I'm not going to bother to simplify that, but you can if you would like to. And so now we have all the information that we need to figure out what dC dt is, which is how fast the distance between the two boats is increasing after 2 hours. That's equal to A, which is 22, times dA dt, which is 11, plus B, which is 16, times dB dt, which is 8, all over C, which is the square root of 22 squared plus 16 squared. Okay, So that's how you do that. I'll just kind of quickly mention that there are, again, multiple ways of going about doing this problem. One thing that you could do is actually get a formula for what a and b are equal to in terms of t. So we don't really have any t's floating around in this equation, but you could say that just a is equal to 11 t and b is equal to 8t, depending on what t is. And then dA dt is still going to be 11, dB dt is still going to be 8. You could figure out what c is actually in terms of a and b. It's just going to be the square root of this squared plus this squared. And then plug all your information in that way. And that way you would actually have like less variables floating around in your problem. But you don't necessarily have to do that. The point of what I'm trying to say here is, again, multiple ways of getting to that same final answer. And there's advantages and disadvantages to each of those ways. So just kind of go with whatever way makes the most sense to you.